When you think about cold, you almost always do so from the body, from a direct and everyday experience, from the memory of a very early morning when the ground is rigid beneath your feet and the air enters your lungs as if it were denser. When your breath becomes visible and the world seems to move more slowly, because cold is not just a temperature, it is a complete sensation. It is the sound that fades, the gesture that withdraws, the immediate impulse to seek shelter. And without realizing it, that very human way of understanding cold becomes the first filter through which you try to imagine the universe. Because everything you know about cold is born here, on the surface of a warm, relatively stable planet, protected by an atmosphere that acts like an invisible blanket. Even so, even within that refuge, cold has always been a warning, a gentle boundary that signals that beyond it, the rules change. From the moment human beings lifted their gaze, the night sky became associated with cold, not because they could touch it, but because it was enough to observe it in silence, to feel the temperature drop, to feel activity cease, to feel fire become central, and warmth turn into something that had to be protected. Ancient cultures did not speak of degrees or absolute scales, but they clearly understood the difference between what preserves life and what extinguishes it, between what flows and what stops. The emptiness of the sky was perceived as distant, inhospitable, alien, a place where one cannot breathe, and that primitive intuition, far from being wrong, was surprisingly accurate. It simply did not yet have the words to explain itself. When you look at the stars from Earth, they seem fixed, eternal, as if they had always been there and always would be. But at the same time, they seem cold, points of light suspended in a deep darkness. Night does not burn, it does not scorch. Night cools. And that association was etched into the human mind for millennia. The sky as a space where heat does not belong, where everything is still, where time stretches and sound dies. That image runs through myths, religions, and poetry, because emptiness has always unsettled human beings, and cold was its most immediate sensory translation. For centuries, the void was not understood as absence, but as something impossible. It was thought that nature abhorred a vacuum, that there always had to be something filling everything: air, ether, spirit, divinity. Cold, then, was not seen as a lack of energy, but as a mysterious, almost active quality, a force that extinguished, that put to sleep, that stopped. On Earth, cold freezes water, hardens the ground, makes life fragile, so it was natural to imagine that if there were a truly empty place, that place would have to be profoundly cold, a space where nothing moves because nothing can be sustained. Even when science began to measure, to classify, and to experiment, cold remained a frontier. Reaching lower temperatures always meant approaching a limit, a kind of invisible edge where matter behaves in strange ways. Meanwhile, the sky remained up there, silent, black, apparently motionless, a constant reminder that, no matter how much the human world filled with noise and heat, there existed an immense environment where those conditions were exceptions, not the rule. From Earth, the universe is imagined first as distance, then as darkness, and finally as cold. It is an almost inevitable sequence. First, you understand that it is far away, so far that you cannot reach it. Then you accept that it is dark, because most of the time it does not emit visible light. And finally, you intuit that it must be cold, because there are not enough suns, nor atmospheres, nor surfaces that retain heat the way this planet does. That intuition, born of the most basic human experience, is the starting point for understanding something much deeper. that cold is not a cosmic rarity, but the natural state of the universe, and that the heat you know is a fragile, local, and temporary exception. And right there, exactly there, the true journey begins. Now imagine that you slowly move away from Earth, not suddenly, not like a violent ejection, but calmly, as if the planet were shrinking beneath your feet while you remain suspended. First, the familiar sounds disappear, the distant murmur of the city, the wind, even that constant hum you never notice until it is gone. Then the blue sky grows darker, loses depth, flattens, and the air becomes so thin that it stops being something you breathe and becomes a memory. At that point, you begin to understand that space is not just a place without things, but an extreme thermal frontier, an absolute limit where heat stops behaving as you know it, and silence stops being an idea and becomes a permanent condition. Here on Earth, silence is never total. There is always a background, a minimal murmur, an imperceptible vibration. The ground transmits waves. The air is never completely still. The body itself makes noise without asking permission. Even on a deep night, far from everything, the planet is still alive, and that constant movement generates heat, because heat is that, movement, friction, continuous exchange. But when you leave the atmosphere, that entire system shuts down abruptly. There is no air to vibrate, not enough particles to carry sound, no medium to connect one thing to another. For the first time, silence is not psychological or emotional. It is physical, absolute, non-negotiable. Stop for a moment and think about what that means for you as an observer, because everything you know about the world happens in the presence of sound. Even when you think you are in silence, your brain is still receiving signals. In space, it is not. There is no echo, no sonic distance, no warning. An explosion happens without a bang. A collision does not scream. A catastrophe has no soundtrack. The universe does not accompany events with noise, and that total silence is not comforting. It is strange, almost unnatural for a mind that evolved surrounded by stimuli. And along with silence comes cold, not as a gust or a shiver, but as a constant condition. Space is not cold in the same way a mountain or a winter night is cold. There is no icy air brushing the skin. There is something more radical, the almost total absence of available thermal energy. The temperature of deep space approaches a limiting value, just a few degrees above absolute zero, a boundary where the microscopic motion of matter is reduced to the minimum allowed by physical laws. That number, which on Earth would be incomprehensible, is the backdrop of the entire universe. Down here, heat is conserved, transferred, trapped. The ground stores energy from the sun during the day and releases it at night. The oceans act as enormous thermal reservoirs. The atmosphere distributes and softens extremes. But when you leave that protective system, heat no longer has anywhere to stay. It radiates, it is lost, it disperses in all directions. In space, any object that does not produce energy on its own tends to cool, not because something cools it, but because there is nothing to keep it warm. Imagine your body floating there, protected only by an artificial layer, while the heat you generate constantly tries to escape. It is not that space freezes you like a refrigerated chamber. It is that it steals your heat without resistance, without effort, simply letting it go. The cold of space does not attack, does not push, does not invade. The cold of space is indifference, and that indifference is perhaps one of the hardest ideas to accept because you are used to thinking of cold as a presence, when in reality it is an absence. The universe, seen from this perspective, is not hostile in the human sense. It has no intention. It does not punish. It simply exists under rules where heat is rare and silence is permanent. Energy concentrates only in specific points: stars, planets, active regions. Everything else is background, stillness, thermal equilibrium near the minimum. And you, as an observer, as an inhabitant of a small, warm bubble, are a statistical exception walking on another exception. When the first scientists began to think of space as a real place and not a philosophical concept, this idea was profoundly unsettling. The sky had been imagined as filled with ether, with some invisible medium that supported everything. Accepting that space could be almost empty, silent, and cold meant accepting that the universe was not designed to accompany life, but that life had to carve its way through conditions alien to it. Cold ceased to be an accident and became the norm. From Earth, you have always lived surrounded by layers: atmospheric layer, magnetic layer, thermal layer. Each one filters, cushions, and translates the environment so that it is habitable. In space, those layers disappear. What remains is the base state of the cosmos, a state where temperature does not fluctuate with seasons, where there are no sunrises or sunsets, where heat does not accumulate and silence does not break. Now think about the concept of a limiting temperature. On Earth, you can always imagine something colder: a cave, a glacier, the bottom of the ocean. But space introduces a different limit. There exists a theoretical minimum temperature, a point at which thermal energy cannot decrease any further. It is never fully reached, but it is approached. The universe moves around that value like a constant whisper. That thermal background is a trace of the origin, a distant echo of a much hotter past. But today, it manifests as a cold calm that envelops everything. And the most unsettling thing is that this cold does not depend on distance from a star or proximity to a planet. Even in regions that seem empty, far from everything, there exists a residual, uniform temperature, almost identical in all directions. The universe does not cool chaotically. It does so in an orderly way, as if it were slowly relaxing after a gigantic effort. That effort occurred so long ago that only this thermal whisper remains, this minimal warmth that defines the lower limit of cosmic heat. As an observer, this places you in a strange position. You are accustomed to associating cold with death, with immobility, with an ending. But the cold of space is not an ending. It is a stage. It is the background against which all the energetic stories of the universe unfold. Stars shine because they struggle against that background. Planets maintain temperatures because they are trapped in fragile equilibria. Life exists because, for a moment, in a small place, heat manages to stay. The absolute silence of space accompanies this thermal state as its perfect complement, without sound, without friction, without exchange. Everything happens without auditory witnesses. The most violent events in the cosmos, explosions that release more energy than thousands of suns, occur in total silence. You would not hear them, even if you were there. You would only see light, motion, deformation. The universe does not narrate its actions. It simply carries them out. And here is where your imagination begins to change. Cold stops being a threat and becomes context. Silence stops being emptiness and becomes language. Space is not dead. It is still. It is not frozen. It is balanced. And you, in thinking about this, begin to understand that everything warm, everything sonorous, everything alive happens against an immensity that does not need noise or heat to exist. This is the true thermal limit of the universe. Not a wall, not an edge, but a constant condition. A state where energy is scarce, where motion is minimal, and where silence is not a pause, but the rule. And from there, from that cold and quiet background, everything that has ever shone emerges. Now imagine that all the cold we have been talking about is not just a consequence of the present-day universe, but a trace, a thermal memory that permeates everything, as if the entire universe still preserved the mark of a completely different past. Because before being this silent and almost motionless place, the universe was the opposite. It was dense. It was brilliant. It was unbearably hot. And the most astonishing thing is that this story is not lost. It is not a poetic conjecture. It is still here, surrounding you at this very moment, passing through your body without you noticing, like an ancient whisper that never faded. If right now you could see beyond your senses, you would discover that space is not completely empty. It is filled with an extremely weak, uniform, gentle radiation that arrives equally from all directions. No matter where you look, no matter how far you point your instruments, that signal is always there. It is the cosmic microwave background. It is not visible light. It does not illuminate. It does not warm your skin. It is a kind of thermal echo, the oldest photograph of the universe, taken when everything that exists today was just beginning to cool. To understand what you are observing, you need to change the scale of your imagination. You have to stop thinking about stars, planets, and galaxies, and start thinking about a universe so young that nothing of that existed yet. A universe with no structures, no forms, no empty spaces. Everything was compressed, mixed in thermal equilibrium. The temperature was so high that matter could not organize itself. Atoms did not exist. Light could not travel freely. Everything collided with everything else, constantly, in a chaotic and brilliant dance. In that primordial state, the universe had no cold or hot regions. On average, it was the same everywhere. And you have to make a tremendous effort to accept this idea, because you are used to a world full of contrasts. But the young universe was almost perfectly uniform. That uniformity is key, because what we observe today as the cosmic background is the cooled remnant of that initial state. As the universe expanded, it began to cool, not because something external cooled it, but because as it expanded, energy was distributed over an ever greater volume. It is as if you had a glowing ember and spread it out until it filled an entire room. It does not disappear. It simply dilutes. That is what happened to the primordial heat. Over time, the temperature dropped enough to allow matter to organize itself. Electrons could join nuclei. Atoms were born. And at that moment, light was set free. That instant is crucial because it is the moment when the universe became transparent. Before that, radiation constantly collided with charged particles, unable to move forward. Afterward, light began to travel without obstacles, expanding along with space itself. That light, stretched by billions of years of expansion, is what we detect today as microwaves. It is not a signal created later. It is the same light, aged, cooled, stretched, but intact in its essence. Stop for a second and think about this, because it is one of the deepest ideas you can experience. When instruments detect the cosmic microwave background, they are not seeing a simulation or a reconstruction. They are seeing the past directly. They are capturing photons that began their journey when the universe was only a few 100,000 years old. Photons that have traveled without rest, crossing the expansion of space until reaching here, until passing through you. That thermal background has a very precise temperature, just a few degrees above absolute zero. And that temperature is almost the same in all directions. That extreme uniformity is one of the strongest pieces of evidence that the universe had a hot, dense origin. It is not a coincidence. It is not chance. It is a physical, measurable, persistent trace. And yet, within that almost perfect uniformity, there are small variations, tiny differences, 1 part in 100,000, changes so subtle that at first they seemed like measurement errors. But those small irregularities are actually the seeds of everything that exists today. They are the thermal wrinkles of the primitive universe, regions slightly hotter or colder that over time gave rise to galaxies, clusters, stars, and planets. It is here that the cosmic background stops being just proof of the past and becomes a map of the future. Those tiny differences indicate where matter was just a bit denser, where gravity had a little more influence. Over millions of years, those regions grew and grouped, collapsed. Everything you see in the night sky was born from those almost invisible imperfections. This idea places you before a beautiful paradox. The universe that you perceive today as cold, dark, and silent preserves in its most basic structure the memory of a blazing, luminous birth. The cold that dominates the cosmos is not forgetfulness but consequence. It is the natural result of prolonged expansion. The cosmic background is the thermometer that never turns off, the signal that confirms that everything began under extreme conditions. And there is something even more unsettling. That background is not static. It continues to cool. As the universe continues to expand, the wavelength of that radiation stretches a little more. The temperature slowly drops. The universe moves ever farther from its hot origin. The cosmic background becomes colder, weaker, harder to detect. But it is still here. You can still measure it. You can still listen to it if you know how. Think about how extraordinary this is. In a universe so vast, so ancient, so indifferent, there exists a signal that directly connects the present with the beginning. You do not need to travel through time. You do not need to leave your era. The past is superimposed on the present, traveling along with it. And you, from this small, warm point, have the ability to detect it. The cosmic background also redefines what you understand by cold. It is not just the absence of heat. It is the final state of a thermal story. It is the residue of a universe that is slowly cooling, like a bonfire that no longer has fuel, but still emits an almost imperceptible warmth. That residual heat is enough to fill all of space. It is the baseline level upon which all current processes occur. When you think about the silence of space and its limiting temperature, you can now add another layer. Space is not cold only because it is empty, but because it remembers, because it still retains the energy of a beginning that has been dissipating for billions of years. The cosmic background is that memory turned into temperature. And as you continue listening to this story, as you imagine that invisible sea of radiation enveloping everything, you begin to understand that the universe does not exist only in the present. It lives in superimposed temporal layers. The past does not disappear. It cools and stretches. It becomes almost imperceptible, but it never goes away completely. There, in that thermal whisper that fills space, is written the oldest story we can read, a story that needs no words, no images, no sound. Only temperature, a faint signal that reminds you again and again that even in the deepest cold, the origin is still present. Now I invite you to take one more step back, even further back, to a moment when even that cosmic background that now permeates everything was intensely bright, when the universe knew neither cold nor silence because there was simply no space for them to exist. Imagine a cosmos so young that the word space barely makes sense. A universe where everything was so close to everything else that the idea of distance becomes useless. Where every region was so full of energy that there was no room for stillness, for emptiness, or for thermal rest. In that early universe, there were no stars, no galaxies, no light traveling freely for millions of years. There was something much more radical. There was a dense, blazing soup of elementary particles, radiation, and energy, all mixed together in an extreme state. And when I say extreme, I want you to feel it, to imagine it not as a localized explosion, but as a global condition. There was no hot center surrounded by cold regions. Everything was hot. Everything was compressed, and everything was constantly interacting. You, as an observer, must abandon for a moment the idea of objects floating in space, because in that initial instant space itself was being born. The universe was not expanding into something, it was expanding with itself. Every point was moving away from every other, not because they were traveling through a fixed stage, but because the stage itself was stretching. This is one of the most difficult ideas to assimilate, because it contradicts everyday intuition. But it is essential to understanding why the young universe was so hot, and why that heat was inevitably destined to dissipate. When the universe was young, its density was immense. That means an enormous amount of energy was concentrated in a tiny volume. And where there is density, there are collisions. Where there are collisions, there is exchange. And where there is constant exchange, there is temperature. The heat of the primordial universe did not come from stars or organized nuclear reactions, but from the fact that everything was colliding with everything else, all the time, without rest. It was a state of total agitation. In that context, the notion of solid matter or even stable particles made no sense. The energy was so high that any attempt at organization was immediately destroyed. Protons and electrons could not bind together. Atoms could not exist. Light could not travel without being absorbed or scattered. The universe was opaque, brilliant, almost blinding in physical terms, even though no eyes existed to see it. Stop for a moment and think about how counterintuitive this is. Today you associate youth with fragility, with small size, with lack of energy, and the young universe was the opposite. It was powerful, dominant, excessive. Its youth was marked by an excess of energy, not by its absence, and that excess is precisely what drove its transformation. As the universe began to expand, something fundamental happened. It was not an explosion that hurled fragments outward from a central point. It was a homogeneous, uniform expansion. Every region moved away from every other at the same time. And that expansion had an inevitable consequence: cooling. As the available volume increased, the average energy decreased. Heat did not disappear. It was distributed. It was stretched. It was diluted. This process was neither instantaneous nor chaotic. It was gradual, continuous, relentless. Second by second, the universe became a little larger and a little colder. And within that thermal descent, crucial transitions occurred. Like invisible steps, the cosmos descended one by one. Each step downward allowed something new to exist. First, the most elementary particles were able to stabilize. Then protons and neutrons began to form nuclei. Later, when the temperature dropped enough, electrons were able to bind to those nuclei, giving rise to the first atoms. Each of these steps depended on the universe cooling. Heat, which at first dominated everything, began to give way to structure. As an observer, it is important for you to understand that this cooling was not a loss, but a release. Extreme heat prevented complexity. Only when energy dropped below a certain threshold could matter organize itself. The universe did not become interesting despite cooling, but because of it. Expansion, then, is not just a geometric feature of the cosmos, it is the engine of its history. Without expansion, the universe would have remained in a uniform, hot, chaotic state. There would have been no stars, no galaxies, no chemistry, no life. Expansion created thermal time. It created a sequence of possibilities. And here appears an idea that completely changes how you understand the current coldness of the universe. Cold is not the original state, it is the result. The universe was not born cold, it became cold. And that cooling is not an anomaly, it is the natural consequence of a cosmos that expands without end. When you look at the sky today, you are seeing a universe that has had billions of years to lose heat. A universe that has gone from an unbearably hot state to one where heat is rare and localized. Stars are relics of that energetic past. They are regions where energy is still concentrated, where the universe briefly remembers what it was like in the beginning. But even those islands of heat are destined to fade. Expansion continues. Cooling continues. The young universe was full of available energy, and the present universe lives on leftovers, on temporary concentrations and fragile equilibria. Now think about density. In the early universe, density did not vary much from place to place. Everything was compressed. Today, by contrast, the average density is extremely low. The space between galaxies is almost empty. Matter is dispersed into structures separated by enormous distances. This radical change is the direct result of prolonged expansion. And yet there is a deep continuity between that young, hot universe and the cold cosmos you inhabit today. They are not two different universes. It is the same one at different stages of its thermal history. The cosmic microwave background is the bridge between the two. It is proof that the initial heat did not disappear without a trace. As an observer, this understanding places you on a timeline that cuts through everything. You are living in a universe that is still cooling, still expanding, still transforming. You are not in a final state. You are in an intermediate moment, a moment in which heat still exists, but no longer dominates. The young universe knew no silence because interactions were constant. It knew no cold because energy filled everything. The present universe, by contrast, is defined by vast silent and cold regions, interrupted by pockets of activity. That contrast is the very history of the cosmos, written in temperature and density. And as you continue listening, as you imagine that blazing past slowly transforming into the present stage, you begin to perceive cold not as a threat, but as a sign of cosmic maturity. The universe has lived long enough to calm down, to disperse its energy, and to allow quiet places to exist where something like you can stop and observe it. The journey is not over. Key stages in this thermal history still remain. It still remains to understand how that almost uniform universe began to break its symmetry, how the first irregularities arose, how cold allowed gravity to take center stage. But now you know this: the cold of the universe is not an accident. It is the inevitable result of a hot birth and an expansion that never stopped. And you, from this small warm point, are a witness to that continuous transformation. Now imagine that the young universe we have been talking about begins to cross a silent threshold. one announced not by explosions or flashes, but by something far more subtle, a gradual decrease in temperature that changes the rules without making noise. There is no exact instant when everything transforms at once. It is more like the coming of night, when you cannot point to the precise second the day ceased to exist. Cooling works that way, patiently and constantly, allowing the impossible to become possible without asking permission. At first, when the universe was too hot, matter could not hold together. Particles collided with such violence that any attempt at organization fell apart instantly. It was like trying to build something delicate in the middle of a storm. Everything separated, everything dispersed. Extreme heat did not favor complexity, it annihilated it. And here you need to adjust your intuition, because we tend to think of energy as something creative. But when it is excessive, energy also destroys. As the universe expanded and cooled, the intensity of those collisions began to decrease. They did not disappear, but they became less aggressive, more spaced out. And that very small change altered everything. For the first time, some particles could remain together long enough to form something more stable. Protons and neutrons began to cluster into simple nuclei. It was not yet matter, as you know it, but it was the universe's first attempt at organization. Stop here for a moment and think about how delicate this process was. It was not automatic or inevitable. It depended on the temperature dropping just enough. A little hotter and nothing would have remained bound. A little colder and the story would have been different. The universe advanced along a very narrow band of conditions, like walking a thermal tightrope without yet knowing everything it was about to allow. For a long period, those nuclei coexisted with a sea of free electrons and intense radiation. The universe was still opaque. Light could not travel far without colliding, without getting lost, without being absorbed. Everything was trapped in constant interaction. There was no distance, no horizon, no space that could yet be seen. And then, without drama, one of the most decisive moments in all of cosmic history occurred. Cooling reached a critical point. Energy was no longer sufficient to keep electrons separated from nuclei. For the first time, electrons could bind stably to protons. Atoms were born, mostly hydrogen, something extremely simple and, at the same time, profoundly transformative. In that instant, the universe changed forever. As atoms formed, matter ceased to be a chaotic plasma and became neutral. And by becoming neutral, it stopped interacting constantly with radiation. Light, which until then had been trapped, was released and began its journey. The universe became transparent, and darkness, as you understand it today, became possible for the first time. As an observer, this idea carries special weight. Light did not exist as a free messenger until the universe cooled enough. Before that, there were no images, no landscapes, no way to observe. Everything was mixed, confined. Cooling did not only allow matter, it allowed vision. It allowed the universe to begin to reveal itself. That released light is the same light we detect today as the cosmic microwave background. It is direct proof of that moment of transition, when the universe stopped being a hot fog and became a space where things could exist separately from one another. Each of those photons has traveled for billions of years to reach here and pass through you without you noticing. But the process did not end there. Over time, newly formed matter began to feel another influence that until then had remained in the background: gravity. While heat dominated, gravity could organize nothing. It was too weak against thermal chaos. But as the universe cooled, gravity, began to gain ground, slowly, without haste, gathering matter in slightly denser regions. Those small differences were amplified. Where there was a bit more matter, gravity attracted even more, and so clouds of gas began to form. Denser regions, the first embryos of stars and galaxies. And here, cold once again takes a central role, because without cooling, gravity would never have had a chance. Heat separates and disperses. Cold allows things to draw closer and remain together. The first stars were born thanks to this delicate balance. Great clouds of hydrogen contracted under their own gravity and, in doing so, heated up in their interiors until nuclear reactions ignited. It is a fascinating contrast. The cold of the universe allowed matter to concentrate, and that concentration created new pockets of heat. As an observer, you begin to notice a constant dance. The universe cools on average, but it creates islands of energy. It becomes silent, but it allows bursts. Everything you see today, from the light of a star to the warmth of your own body, is an indirect consequence of that initial cooling that allowed matter to exist. Atoms opened the door to chemistry. Inside stars, heavier elements were forged, and when those stars died, they dispersed them into space. New generations of stars and planets formed from that enriched material. All of this immense process has a common root: the drop in temperature that allowed atoms not to fall apart instantly. Light, for its part, became a messenger. No longer trapped, it could travel, inform, connect distant regions of the cosmos. Thanks to that, today you can look at the sky and receive signals from events that occurred millions or billions of years ago. Each ray of light is a story that could only begin to be told when the universe cooled enough to let it pass. Think about how paradoxical this is. Cooling, which we usually associate with extinguishing and endings, was in fact the beginning of everything that matters. Without cooling, there would be no stable matter. Without matter, there would be no structures. Without structures, there would be no stars. Without stars, there would be no complex elements. And without them, you would not be here, listening to this story. The universe did not become interesting despite losing heat. It became interesting because it lost it. Every degree less opened a new possibility. Every descent allowed a different form of organization. Cold was not a wall, it was a door. And as you move forward in this story, you begin to understand that the universe not only expands and ages, it also learns how to cool. And in that learning is written everything that has ever existed and everything that is yet to come. Now imagine that the universe has just crossed one of the quietest and most decisive thresholds in its entire history. There is no explosion, no flash, no conscious witnesses to record it. And yet, from that instant on, nothing is ever the same. The cosmos enters the coldest night it has known up to that point. A night that does not arrive suddenly, but settles in little by little as the universe calms down and learns, for the first time, to let light pass. Up to that moment, the universe had been like a thick, hot fog, an environment saturated with energy, where every attempt at separation was immediately undone. Light existed, but it could not advance. It was born and died again and again over tiny distances, trapped in an endless web of interactions with charged particles. The cosmos was bright in physical terms, but not visible, because there was no distance, no horizon, no clear space where light could draw an image. When cooling reached just the right point, something extraordinary happened without any need for drama. Electrons managed to bind stably to nuclei, and atoms consolidated as complete, electrically neutral entities. That detail, which may seem technical and distant, had a profound consequence. By becoming neutral, matter stopped constantly scattering radiation. Light was set free, and in that very instant, the universe ceased to be opaque and became transparent. Stop here for a moment and try to imagine what that means, because it is not just a physical change. It is a change in the very experience of the cosmos. Before this point, there was no way to see through the universe. There was no background, no observable depth. Everything was so full that information could not travel. After this instant, light began to move unobstructed, carrying with it a frozen image of the young universe, an image that would continue traveling for billions of years. That moment marks the birth of cosmic night, but not a night like the one you know on Earth. It is not a night caused by the rotation of a planet or the temporary absence of a nearby star. It is a deep, universal night, a night that emerges when the universe cools enough to stop shining on its own. It does not extinguish light, it releases it. As an observer, it is important to understand that the darkness of the universe is not a primordial state. It was not there from the beginning. On the contrary, the universe began intensely bright, saturated with energy, almost blinding. Darkness appeared later, as a natural consequence of cooling, when radiation ceased to dominate everything, and matter calmed enough to allow spaces between things. Transparency allowed space to acquire depth. For the first time, there was a here and a there, a near and a far, a visual before and after. Light could travel for hundreds of thousands of years without interruption, creating an observable horizon, a limit from which the universe could begin to be seen, even though there were still no stars or galaxies. That first transparent sky was not filled with bright points. There were no constellations, no recognizable shapes, no sharp contrasts. It was a uniform, soft, enveloping glow, a light arriving from all directions at the same time. The entire universe emitted a homogeneous clarity, a kind of dim radiance that filled all available space. With the passage of time, that light began to change. As the universe continued to expand, light waves stretched, losing energy, shifting toward ever longer wavelengths. What had once been intense, hot light slowly transformed into cold, faint radiation. That process did not stop. It continues even today. That stretched light is what you now know as the cosmic microwave background. It is not a modern invention or a theoretical reconstruction. It is the real light of the universe when it became transparent. It is the thermal imprint of that first night, a signal that continues to travel, silent and uniform, passing through galaxies, voids, and bodies with hardly any interaction at all. Think about how intimate this idea is. While you listen to these words, while you breathe, while your body generates heat, that radiation passes through every centimeter of you. You do not feel it. You do not see it, but it is there. It is the oldest echo we can detect, a constant presence that connects this moment to a past so remote it is difficult to imagine. The coldest night was not an isolated event. It was the beginning of a new stage. From that moment on, the universe was no longer dominated by radiation, but began to be governed slowly by matter and later by gravity. Cooling allowed energy to cease being the main actor and to give way to slower, more structured processes. For a long time after becoming transparent, the universe remained dark in the human sense. There were still no stars to illuminate space. There were no local sources of intense light. It was a vast, deep night, crossed only by the residual glow of the cosmic background, which over millions of years became colder and weaker. This period is, in many ways, the longest night the cosmos has ever known, a stage in which the universe could already be seen, but still had nothing spectacular to show. It was a prepared stage, a dark canvas waiting for its first brushstrokes. As an observer, this changes how you understand darkness. It is not absence, it is waiting. Cosmic darkness does not mean absolute emptiness, but potential. It means the conditions are in place for something new to happen, even if it has not yet begun. Transparency also allowed tiny, almost imperceptible differences to begin to amplify. Slightly denser regions began to stand out against the background. Gravity, now less opposed by heat, began to do its work, slowly, very slowly, on a scale that defies any human notion of patience. As the universe grew darker, its future was taking shape. The seeds of the first stars were growing in silence, hidden in the cold night. The cosmos was not inactive, it was incubating. Meanwhile, the cosmic background continued to cool. Its temperature dropped as space expanded. It went from being visible light to infrared radiation, and then to microwaves. Today, that radiation defines the thermal floor of the universe. It is a constant reminder that even in the deepest darkness, there is a history that has not been erased. This primordial night also redefines the concept of silence. Not only was there no sound, as you already know happens in space, but there were also no obvious signs of activity. There were no stellar explosions, no large-scale violent collisions. The universe passed through a stage of profound calm, a cosmic pause between the initial chaos and future complexity. And as you understand this, you begin to see the universe not as a succession of spectacular events, but as a continuous process, where the most important moments are not always the loudest or the most visible. Sometimes the changes that transform everything happen in silence and in cold. The coldest night was not the end of anything. It was the beginning of the possibility of observation. It was the moment when the universe stopped being just a state and became a visible history. Without that night, without that transparency, there would have been nothing to observe, no signals to detect, no thermal memory to study. Today, every time you look at the sky, you are seeing the consequences of that moment. Even the darkness between the stars is a direct heir of the instant when the universe learned to let light pass through. Cold and night are not enemies of knowledge. They are its condition. And if you have come this far with me, perhaps you begin to feel something different toward cosmic darkness, not as a terrifying void, but as a space filled with the past, a place where the origin still whispers, where the first night continues to stretch, slowly and silently, through time. Think for a moment of a freshly stretched bedsheet. From the doorway, it looks completely smooth, calm, almost perfect. But if you come closer and carefully run your hand over it, you begin to notice small undulations, tiny folds that are not visible at first glance. The universe, after becoming transparent, was very much like that. On large scales, it appeared uniform, silent, serene, but in reality, it was full of small irregularities, tiny wrinkles that barely broke the surface, yet contained enormous power. Those wrinkles were not flaws or mistakes. They were differences so subtle that, had they been a little smaller, the universe might have remained trapped in eternal monotony. They were variations in temperature and density, so small that it is hard to believe that everything you know emerged from them. Galaxies, stars, planets, even you yourself can all be traced back to those almost imperceptible differences. Now imagine a bowl of hot soup just served. If you look at it from above, it seems homogeneous. Everything has the same color, the same texture. But if you wait a bit and watch carefully, gentle currents begin to form. Areas where the heat is just slightly different cause the liquid to move slowly. There is no need for violent boiling. A minimal difference is enough for everything to begin reorganizing. Something very similar happened with the universe. After the great initial expansion and the cooling that allowed light to travel freely, the cosmos was suspended in a deceptive calm. There were no explosions, no flashes, no sounds. But in that stillness, the thermal wrinkles were still there, persistent, marking places where matter had a slight preference for gathering. These differences were extremely small. We are not talking about blazing regions versus frozen zones. We are talking about changes so tiny you would barely notice them if you were there. And yet gravity is very sensitive. It does not need large contrasts. It only needs time. And the universe had time to spare. Where there was a little more matter, gravity pulled with a little more force. Not much, just enough to tip the balance. That small pull caused more particles to drift closer. As they came closer, density increased. And as density increased, attraction grew a bit more. It is a process similar to a snowball rolling downhill. It starts small, almost insignificant, but it keeps growing. In other areas, where matter was slightly less abundant, the opposite happened. Particles tended to drift away, attracted toward neighboring, denser regions. Thus, little by little, the universe began to differentiate itself, not abruptly or chaotically, but with an almost meditative slowness. It was a change that could only be appreciated by observing millions of years at once. You can imagine it like a crowd slowly dispersing across a huge square. At first, everyone is more or less evenly distributed, but it is enough for a few people to stand a bit closer together for others to follow. Over time, small groups form, then larger groups, and between them, increasingly empty spaces remain. No one planned it. It simply happened. This is how the large-scale structure of the universe began to take shape, not as a collection of isolated objects, but as a network. Gigantic filaments of matter stretched through space, connecting denser regions, while enormous voids opened between them. It is a surprising, elegant architecture, and it all began with those almost invisible wrinkles of the young universe. During this stage, the night was still deep. There were no stars lighting up space. The sky, if anyone could have seen it, would have been dark, crossed only by the faint residual glow of the cosmic background. But beneath that darkness, the universe was at work, organizing itself, preparing the stage for something far more complex. Cooling was key to this entire process. Heat tends to disorder, to disperse. Cold, by contrast, allows things to come together and stay together. As the universe lost temperature, matter moved more slowly, making it easier for gravity to do its work. The wrinkles did not smooth out. They became more important. Each of those irregularities acted as a kind of starting point. Some were a little more pronounced, others barely distinguishable. That initial difference set the pace of evolution for each region. Some areas advanced more quickly toward the formation of structures. Others lagged behind, creating a diverse, uneven cosmos full of contrasts. It is fascinating to think that none of this required complex instructions. The universe had no blueprint or prior design. It simply followed simple rules, repeated over and over, across immense periods. Small differences plus time produce large results. It is a lesson that repeats itself at many levels of nature. As the denser regions grew, the gas composing them began to behave differently. As it concentrated, it could cool locally, lose energy, and compress even further. It was a gradual, almost silent process, but essential. Without this local cooling, nothing new could form. Meanwhile, the great voids expanded. They became darker, colder, more extensive. They were not dead spaces, but the necessary complement of dense regions. Like silences in music, they gave shape to the whole. Without them, the structure would lose meaning. All of this happened without haste. The universe had no urgency. Each stage unfolded at its own pace, allowing the consequences of those primordial wrinkles to spread calmly. Millions of years passed, without anything that today we would call spectacular happening. But without those millions of years, nothing spectacular would have happened afterward. What you are following here is not a story of constant explosions, but a story of patience. A story where cold does not extinguish, but preserves. Where darkness does not mean emptiness, but preparation. Where small, almost invisible differences become the foundations of everything that is to come. The wrinkles of the cosmos were, in essence, the universe's first creative gesture. Not a conscious act, not a decision, but a natural consequence of its birth. From them, everything else became possible. The first stars, the first galaxies, the light that would later break the night, all of it originated in those minimal variations. And as you move forward in this story, you may begin to look at imperfection differently. In the universe, what is perfectly smooth creates nothing. It is the small irregularity that opens the path. It is the wrinkle that allows something to grow. So far, you have seen how the universe went from an almost perfectly uniform state to a slightly wrinkled one, like a surface that is no longer completely smooth. Now comes the next step, perhaps one of the most fascinating, because it is the moment when those small differences stop being mere promises and begin to turn into something recognizable. It is the birth of structures, not as a sudden event, but as a slow, inevitable, and profoundly elegant process. Imagine nearly flat ground after a gentle rain. At first glance, it looks uniform, but the water does not stay still. It seeks the lowest points, even if they are only barely lower than the rest. At first, the flow is imperceptible, almost shy. Over time, those small paths become marked, deepen, and before you realize it, grooves, channels, small streams have appeared. No one drew them. The water simply followed the minimal slope available. Something very similar happened with matter in the young universe. The cosmos was still, on average, very homogeneous. There were not yet large contrasts, but the thermal wrinkles had already defined slight gravitational slopes. Matter began to move along those almost invisible inclinations. It did not plunge downward. It slid slowly, accumulating where attraction was just a little stronger. As time passed, those accumulations ceased to be insignificant. Regions with a bit more matter began to stand out against the background. They did not shine, they did not emit light, but they had weight, and that weight mattered. Gravity is cumulative. Each added particle made the region a little more attractive to the next. You can think of this like a conversation that starts with two people and, little by little, attracts more. At first, no one notices the group. Then someone comes closer, listens, stays, then another. There is no announcement or clear signal, but the group grows. In this way, the first concentrations of matter began to form in the universe. These concentrations were not yet stars or galaxies. They were large clouds of gas, enormous reservoirs of hydrogen and helium, spread across vast regions. They were cold, dark, and silent. but they were no longer part of the uniform background. They were something different. They were the first sketches of structure. As these regions grew, the contrast with the rest of space became clearer. The voids became emptier, not because something actively pushed matter out, but because matter left them, drawn toward slightly denser zones. Thus, the universe began to acquire a defined geometry, a kind of invisible skeleton that organized everything that would come afterward. This skeleton did not have simple shapes. They were not isolated spheres floating in nothingness. They were long, thin filaments connecting denser nodes, like a three-dimensional network stretched across all of space. If you could observe it from afar, you would see something like a gigantic spider web, where the threads concentrate matter, and the spaces between them remain almost empty. What is astonishing is that this structure arises naturally. It does not need constant fine-tuning. It does not need external corrections. Once the small initial irregularities exist, gravity takes care of the rest. The universe does not build quickly, but it builds well. Over hundreds of millions of years, the denser regions began to experience internal changes. As gas accumulated, pressure increased. Some areas within these clouds became even denser than others. It was like an earthly cloud beginning to condense in specific parts, forming more compact cores. In these internal regions, the gas could cool more efficiently. As it lost energy, it contracted. And as it contracted, it heated locally. This interplay between cooling and contraction marked the path toward a new kind of structure, one that had not yet appeared in the universe. But before reaching that point, the cosmos had to pass through a prolonged stage of silent organization. Throughout all this time, the universe continued to expand. Distances grew, structures moved farther apart, and yet, local gravity was strong enough to overcome that expansion in specific regions. This is important because it shows that the universe does not evolve uniformly. Some zones drift farther and farther apart. Others cling together, compact, resist dissolving. It is like a mass of dough that is rising. Overall, it expands, but within it bubbles form, denser zones, internal structures that do not disappear with the global growth. The universe, in its expansion, also created internal forms that persisted. This birth of structures was not a single moment, but a long transition. There was no day when the universe stopped being uniform and became structured. It was a gradual process, where each small change prepared the next. The cosmic web became more clearly defined, even though it would still be a long time before the first sources of light appeared. Darkness still dominated space, but it was no longer a homogeneous darkness. It was a darkness with relief. There were deeper, denser, more active regions, though invisible. The universe was ceasing to be a passive background and beginning to become a stage. And here, there is something deeply human in this story. Many times we expect important things to announce themselves with noise, with clear signals, with abrupt changes. The universe shows us another possibility. The most decisive transformations can be slow, silent, and almost imperceptible while they are happening. Structures were born because the universe allowed imperfection, because it did not try to erase its small differences, because cold preserved the wrinkles and time did the rest. Every filament, every accumulation of matter is a direct consequence of that almost uniform beginning that never quite became perfect. As these structures grew, they also began to influence one another. Nearby dense regions could attract material from the same surroundings, competing gently. Some gained more, others less. That dynamic balance defined the future size of the great cosmic structures. None of this happened in a hurry. The universe had no predefined final goal. It simply moved forward following the simplest rules, allowing the consequences to unfold freely. And in that unfolding, complexity emerged. When today you look at an image of the universe on large scales, with galaxies distributed in filaments and clusters separated by enormous voids, you are seeing the final result of this process. You are seeing how an almost uniform universe learned to differentiate itself, to organize itself, to create special places where something new could happen. Up to this point, you have traveled through a universe that cools, organizes itself, and learns to differentiate. Now it is time to pause on an idea that seems simple, but is in fact deep and strange when examined closely. The idea of extreme cold, not the cold you know on a winter night, not even the cold of the most inhospitable places on Earth, but a cold that defies intuition, a cold that marks the very limits of physics. When we think of cold, we usually imagine an absence of heat, ice, immobility. But in the universe, cold is not just a sensation. It is a fundamental condition that defines how matter behaves, how much energy it can exchange, which processes are possible and which are forbidden. Cold is not simply the opposite of heat. It is a measure of the internal motion of things. Here on Earth, even in the coldest place you can imagine, particles are never completely still. They always vibrate a little. They always retain some energy. In space, far from stars and galaxies, something similar happens, but taken to the extreme. Deep space is cold not because it is full of ice, but because it is almost empty. And where there are no particles interacting, there is no way to sustain heat. Imagine turning off all the lights in a city and standing in the middle of an immense plain, with no wind, no noise, no visible movement. The cold you would feel would not come only from the air temperature, but from the absence of activity. Space works in a similar way. Its coldness is a direct consequence of its silence. As the universe expanded, energy was spread across an ever greater volume. It is like spreading a spoonful of butter over a gigantic table. It does not disappear, but it becomes thinner and thinner. The result is a progressive cooling that does not stop. Today, the universe has an average temperature just above absolute zero, that theoretical limit where thermal motion reaches its minimum possible value. Absolute zero is not just a number on a thermometer. It is a conceptual boundary. It represents the point at which no more thermal energy can be extracted from a system. It does not mean total immobility, because even there, quantum laws prevent everything from becoming completely still. But it does mark the coldest state imaginable. The universe, in its deepest and emptiest regions, comes dangerously close to that limit. It does not reach it entirely, but it lives near it. The cosmic microwave background, that faint radiation filling everything, establishes a kind of thermal floor. It is the residual whisper of the origin, a minimal presence that prevents the cosmos from freezing completely. Now, not all of the universe shares that same temperature, and here something fascinating appears. While the average is extremely cold, there are regions where conditions are radically different, places where gravity concentrates matter, where energy accumulates, where extreme cold coexists with points of intense heat. The universe does not choose a single state. It allows contrasts. Think of a winter night by a campfire. A few meters from the fire, the air is warm, even pleasant. One step farther away, the cold dominates again. Space works the same way. In the great voids between galaxies, the cold is deep, almost absolute. Inside dense structures, the temperature can rise significantly. The most extreme regions of the universe are not only the hottest, they are also the coldest. The great cosmic voids, those areas where there is almost no matter, are some of the coldest places that exist. There, the absence of particles means an absence of interactions, and without interactions, heat cannot be sustained. These voids are not small, they are enormous. They can stretch across hundreds of millions of light years. They are like oceans of nothingness, where time passes without leaving a visible trace. In those places, the temperature approaches the minimum allowed by physics. There are no active processes, no nearby energy sources, nothing to break the thermal silence. And yet, even that extreme cold is important. It is not a mistake of the universe. It is a natural consequence of its expansion and its structure. Voids allow dense regions to be defined more clearly. They are the necessary contrast that allows structures to stand out. Like the spaces between notes in a melody, they give meaning to the whole. The concept of absolute cold also forces us to rethink the idea of limits. In everyday experience, it always seems possible to cool something a little more, but physics says otherwise. There is a point at which no more thermal energy can be extracted without changing the very nature of the system. That limit is not arbitrary. It is deeply tied to the laws that govern the universe. In its evolution, the cosmos seems to move constantly toward the colder states on average, not because it seeks cold, but because expansion dilutes energy. It is an irreversible process. Heat disperses, differences smooth out, and the universe as a whole cools slowly. This global cooling is one of the clearest arrows of time we know. But at the same time, the universe allows islands of activity to arise, regions where gravity concentrates matter and energy, creating local contrasts. It is a constant dance between dispersion and accumulation. Cold dominates the general stage. Heat appears in localized pockets. This balance is delicate. If the universe had been too hot for too long, structures would not have been able to form. If it had been too cold too early, matter would have frozen into a sterile uniformity. The fact that extreme regions exist, both cold and hot, speaks of a finely balanced history, though not a designed one. When you think about absolute cold, do not think of it as an enemy of life or complexity. Think of it as the silent background that allows contrasts to exist. Without a universe that is mostly cold, there would be no gradients, no flows of energy, no interesting processes. Cold is the stage. Heat is the actor. Even now, as you listen to this story, the universe continues to cool, not in a dramatic way, not perceptible on human scales, but constantly. Stars slowly fade, radiation stretches, energy dilutes. The cosmos is heading toward an increasingly cold and a dark future, but that future does not invalidate the past. On the contrary, it makes it more valuable. Every structure, every star, every planet is a temporary exception in a universe that tends toward cold. They are moments of concentration, of activity, of difference, made possible by a precise balance between expansion and gravity. Extreme regions remind us that the universe is not homogeneous in its experience, even if it is so on average. There are places where cold is so deep that time seems frozen, and others where energy is so intense that the laws of physics are pushed to their limits. The concept of absolute cold, then, is not just a scientific curiosity. It is a key to understanding where the universe is going and why the present is a special moment. We live in an era in which contrasts still exist. where cold has not yet won everything, where structures still shine. At this point, the universe is no longer just a cold, dark expanse with slight irregularities. It begins to resemble a landscape of sharp contrasts, filled with active zones and others that are almost deserted, regions where matter gathers and places where almost nothing remains. Here, three protagonists enter the scene, coexisting and influencing one another: nebulae, vast voids, and an expansion that not only continues, but accelerates. Imagine for a moment observing a city from an airplane at night. You see densely lit areas full of activity, and between them dark stretches with barely any lights. On large scales, the universe looks very much like that. Nebulae would be the neighborhoods under construction, places where matter concentrates and transforms, while voids would be those enormous unlit areas, silent expanses separating one region from another. Nebulae are not small or delicate objects. They are enormous clouds of gas and dust, stretching across immense distances. They are formed mainly of hydrogen and helium, the simplest and most abundant elements in the cosmos, but they also contain traces of other materials that will accumulate over time. They are cold by human standards, but compared to the deep vacuum surrounding them, they are true refuges of matter. You can think of a nebula as a thick cloud in an otherwise clear sky. It does not always shine on its own. Sometimes it merely reflects nearby light. Other times it absorbs it and creates dark silhouettes. But it always marks a place where something is happening, where matter has chosen to gather rather than disperse. These regions do not appear at random. They arise at the nodes of the cosmic web, where filaments of matter converge. Gravity acts like a patient magnet, drawing gas in over millions of years. Little by little, these clouds grow, becoming denser and more complex. There is no rush. The universe continues working at its own pace. Meanwhile, around them, the great voids continue to expand. These voids are not small gaps between structures. They are colossal regions where matter is extremely scarce. In them, galaxies are rare and filaments almost non-existent. They are the quietest and coldest places in the observable universe. To help you visualize this, think of a sponge. The solid part represents dense regions, nebulae, galaxies, clusters. The holes in the sponge represent the voids. They are not artificial additions. They are a natural consequence of how matter is distributed. As the universe expands, it has separated these regions further, making the voids larger and more defined. Something important happens here. As voids grow, the expansion of the universe not only continues, but becomes dominant. For a long time, gravity tried to slow that expansion, at least locally. In dense regions, it still succeeds. But on large scales, something begins to tip the balance. The accelerated expansion of the universe is one of the most perplexing phenomena we know. Galaxies are not only moving away from one another, they are doing so faster and faster. It is as if space itself were stretching more intensely as time passes. To understand this better, imagine drawing dots on a deflated balloon. As you slowly inflate it, the dots separate. If you keep inflating it, not only do they separate more, but the speed at which they separate increases. No dot moves on its own. It is the surface that changes. Something very similar happens with the universe. This process has a direct effect on nebulae and voids. Dense regions continue to evolve internally, but they become increasingly isolated from one another. Voids, for their part, expand more easily because there is less gravity to resist the stretching of space. In a sense, they are the places where expansion expresses itself most freely. You can imagine voids as enormous elastic zones. Because they are not filled with matter, they stretch without resistance. This causes structures to move even farther apart, reinforcing the contrast between fullness and emptiness. The universe becomes more fragmented in terms of activity, even as it remains coherent as a whole. Nebulae, meanwhile, become true cosmic laboratories. Within them, gas is not distributed uniformly. There are vortices, denser regions, areas that begin to collapse under their own gravity. At those points, the story you have been following is about to take an important turn, even though we have not yet reached the light of the first stars. It is interesting to note how cold and expansion play a dual role. On one hand, they cool the universe overall and separate structures. On the other, they allow matter in specific regions to concentrate enough to challenge that global cooling. It is a delicate, almost poetic balance. The universe expands and cools, but at the same time creates islands of complexity. If you think again of the nighttime cityscape, lights are not distributed uniformly. They cluster where conditions allow. The rest remains dark. The universe does something very similar. Nebulae are those points where matter says, here it is worth staying. Accelerated expansion also changes the way the universe relates to itself. Over very long timescales, distant regions will cease to be observable from one another. Not because they disappear, but because expansion will be so rapid that light will no longer be able to cross the distance. Each structure will, in a sense, become enclosed within its own environment. This is not something that will happen tomorrow, or even thousands of years from now. It is a slow but constant process, and yet it is already underway. The universe of the future will be a place where great distances matter more than ever, where voids dominate the total volume, and where active regions become isolated oases. In that context, nebulae take on special value. They are reservoirs of matter in a universe that tends to dilute everything. They are places where history can still continue, where gravity still has something to say. Each one is a reminder that the cosmos is not only expansion and cooling, but also concentration and transformation. At the human level, this idea is surprising. We live surrounded by solid objects, by proximity, by constant interaction. The universe, by contrast, is mostly empty. Most of its volume is occupied by regions where almost nothing happens. And yet it is precisely that vast silence that allows active zones to exist without interfering with one another. Accelerated expansion does not destroy structures that have already formed. It does not tear stars out of galaxies or dissolve local nebulae. It acts on larger scales, separating entire systems. It is an expansion that respects close bonds and stretches distant ones. A selective expansion, one might say. As you follow this story, you may begin to notice a recurring pattern. The universe does not operate through absolute extremes, but through balances. Cold and heat, emptiness and density, expansion and gravity. None wins completely. All coexist, defining different stages of cosmic evolution. Nebulae are testimony that even in a universe dominated by emptiness, matter can organize. Voids are proof that expansion is real and powerful. And acceleration reminds us that the cosmos is not static, that it continues to change even now. After traveling through a universe that expands, cools, and empties, an impossible to ignore contrast appears. While the cosmos on average remains cold, dark, and silent, points begin to ignite where exactly the opposite occurs. Places where cold ceases to rule and matter compresses. agitates, and heats to levels that defy all intuition. Imagine an endless polar night, a landscape covered in ice where the air seems frozen and cold dominates everything. And suddenly, in the middle of that frozen expanse, an intense, steady bonfire appears, capable of melting the ice around it. This is how a star is born in the early universe, as a source of extreme heat ignited in an ocean of deep cold. The contrast could not be greater. The space between stars remains at temperatures close to the minimum possible. Immense regions exist in a cold that barely allows movement, and yet, within some nebulae, the story changes completely. There, gravity has gathered so much gas that pressure increases, density grows, and collapse becomes inevitable. Not violently, but steadily, patiently, like a breath that grows deeper and deeper. You can imagine it as a crowd gradually pressing into a confined space. At first there is freedom, then friction appears, then heat, and finally a sense of contained energy. In the heart of a dense cloud, something very similar happens. Atoms collide more frequently, move faster, and the rise in temperature emerges as a natural consequence of compression. This heating is not superficial or fleeting. It is a continuous escalation. The more the cloud contracts, the hotter it becomes, and the hotter it becomes, the more internal energy it accumulates. A constant tension is established between two opposing forces: gravity, pushing inward, thermal pressure, trying to resist. For a time, neither wins completely. The balance is fragile, unstable, sustained only by the slow passage of time. When the core reaches sufficiently high temperatures, something entirely new happens. Atoms no longer merely collide, they begin to fuse. Hydrogen nuclei join and release enormous amounts of energy. In that moment, a star is born, not as a sudden explosion, but as a gradual ignition, a light that asserts itself and endures against the cold that surrounds it. Here the contrast becomes overwhelming. At the center of a young star, temperatures reach millions of degrees, while around it the universe remains barely above absolute zero. The difference is so great that it is hard to grasp. It is as if, in the midst of the coldest void, a cosmic furnace appeared, completely defying its environment. This contrast is not an isolated oddity. It is a fundamental feature of the universe. Deep cold allowed structures to form, matter to gather without being dispersed by energy. But once that gathering crossed a certain threshold, heat returned with brutal intensity. The universe did not choose between cold and heat. It uses both at different times to build complexity. Stars are not just sources of light. They are thermal engines. They radiate energy into their surroundings, heat nearby gas, and modify local conditions. Where a star is born, the landscape changes. Cold retreats, at least locally. Hot bubbles appear, shock waves, active regions where gas becomes ionized and more energetic. It is as if the universe, for the first time, began turning on lights and heating in a house that had until then been dark and frozen. But that dominance of heat is local and fragile. Just a few light years from a star, temperature drops dramatically again. Space does not retain heat. There are no walls, no air to hold it in. Energy escapes, disperses, dilutes. Each star is a thermal island surrounded by a sea of near absolute cold. This play of contrasts defines the experience of the cosmos. Extremely hot zones coexist with extremely cold regions, separated by distances that are inconceivable to us but are simply part of the landscape for the universe. The result is an uneven, dynamic environment filled with silent tensions. Think of a city seen from very far away at night. Points of light appear scattered, separated by large dark areas. Each point is activity, energy, heat. The rest is silence. On large scales, the universe looks very much like that. Stars are beacons lit in a cold, dark ocean. This contrast has profound consequences. Stellar heat allows complex chemical reactions, the creation of new elements inside stars, and enables the universe to move beyond being composed only of the simplest ingredients. Cold, by contrast, preserves, stabilizes, and allows those products to travel, accumulate, and survive without disintegrating. Without deep cold, heat would be chaotic and destructive. Without stellar heat, cold would be sterile and repetitive. The history of the universe is, to a great extent, the history of this tense and productive balance. The first stars were especially intense, formed in an almost pristine universe. Without heavy elements, they reached enormous sizes and extreme temperatures. They burned with tremendous force and lived short lives. But during that brief existence, they transformed their surroundings in radical ways. They heated the surrounding gas, emitted radiation capable of breaking atoms, and began to erode the cosmic night. Each star was a local rupture of the dominant cold, an assertion of energy in a universe tending toward cooling. And although their light took millions of years to travel, their cumulative effect was deep and lasting. Even so, cold never disappeared. Even in regions where stars were born and died, there were thermal shadows, protected zones where gas remained cold and dense, ready to participate in new stages of the process. The universe does not advance by eliminating previous states, but by layering them. As the universe moves forward, this contrast between the intense heat of stars and the deep cold of space not only persists, but becomes increasingly influential. It is not a decorative detail of the cosmos. It is the silent engine that allows the story to continue unfolding. Cold sets the general rhythm, slow and steady, while heat appears at key moments, concentrated, transformative, almost rebellious against the global tendency toward cooling. Every star that ignites does not live isolated from its surroundings. Its heat spreads, not uniformly, but creating gradients, transition zones where cold and heat meet and interact. At those edges, something special happens. The gas is neither completely frozen nor fully ionized. It is in an intermediate state, active enough to react, yet stable enough to persist. It is at these boundaries that complexity begins to gain ground. You can imagine it like dawn on a winter morning. Not everything warms at the same time. There are places where ice begins to melt while others remain frozen. Puddles appear, small currents, local transformations that would not have been possible either in deep night or in full daylight. The universe works in a similar way. The boundary between stellar heat and deep cold becomes a creative space. As stars evolve, their influence expands. Stellar winds push surrounding gas, creating hot cavities surrounded by colder material. Stellar explosions hurl energy and new elements into space, altering regions that were once quiet. Thermal contrast intensifies. The universe ceases to be a static stage and becomes a dynamic place where heat erupts, cold responds, and both constantly reorganize. These interactions do not only affect the immediate present, they prepare the future. Material heated by stars can later cool and collapse again, now enriched with new elements. Cold allows that material to be preserved, to travel long distances without losing its identity. In this way, thermal contrast does not destroy, it recycles. It is important to note that despite the presence of stars, the universe remains mostly cold. Most of its volume is dominated by regions where almost nothing visible happens. That cold background acts as a buffer. It absorbs excess energy and prevents local processes from propagating chaotically. Without that silent background, every energetic event could disrupt the overall balance. The expansion of the universe reinforces this dynamic. As space stretches, heat dilutes more easily. Stars may shine intensely, but their influence does not extend indefinitely. Cold always ends up reclaiming ground. It is a constant reminder that no energy source is eternal. This balance between heat and cold also defines the cycles of stellar birth and death. Stars are born in cold, dense regions where gravity can act without excessive interference. Once ignited, they generate heat and energy for millions or billions of years. At the end of their lives, they return part of that heat to their surroundings, which then cool again, closing the cycle. Think of a campfire lit with cold wood. It burns for a while, releases heat, transforms matter, and in the end leaves ashes that slowly cool. The universe repeats this process again and again, on immense scales, without haste, without exhaustion. This thermal contrast is also key to understanding why so many different types of cosmic environments exist. Not all stars heat in the same way. Not all cold regions respond to heat in the same manner. From that variety arise different galaxies, diverse stellar systems, cosmic landscapes that are never exactly repeated anywhere. In the long run, the deep cold of the universe acts as a kind of common destiny. Continued expansion ensures that, over time, sources of heat become scarcer. Stars fade, galaxies separate, energy becomes ever more evenly distributed. But even in that distant future, the contrast will have left its mark. The structures formed during the most active eras will continue to exist as memories of a more vibrant universe. What is fascinating is that this contrast not only explains the physics of the cosmos, but also offers a powerful metaphor. The universe progresses not by eliminating extremes, but by allowing them to coexist. Cold does not cancel heat. Heat does not defeat cold. Together, they create the conditions for change. As you continue this story, you may begin to see the night sky differently. Every star you observe is a thermal exception, a point where the universe chose to concentrate energy for a time. Everything else is the cold background that makes it possible. The beauty of the cosmos lies not only in its lights, but in the contrast that surrounds them. Now it is time to pause and focus on something that has always been there, even though you almost never notice it. Something that does not shine like a star, nor burn like the interior of a sun, but that crosses the entire universe without rest. Fossil radiation is the oldest murmur that exists, a permanent whisper that fills space and connects this moment to a past so remote it is difficult to put into words. Imagine entering a room just after someone has left. You do not see the person, you do not hear their voice, but the air still holds their presence. A faint trace of warmth, a subtle scent, a feeling that is hard to define. Fossil radiation is very similar. It is not the origin of the universe itself, but it is the closest thing we can perceive to it. It is the thermal echo of a time when everything was different. When the universe became transparent, light was finally free to travel. That light did not disappear. It was not lost to nothingness. It continues to move, continuing to expand along with space itself. Over time, that light was stretched, losing energy, cooling. What was once an intense glow is now a weak, almost imperceptible radiation, yet omnipresent. This radiation does not come from a specific point in the sky. You cannot point to it with your finger. It arrives from all directions at once. No matter where you look, it is always there. It is like a constant background sound, so uniform that you only notice it once you learn how to listen. And once you do, you can no longer ignore it. To understand it better, think of absolute silence, that silence that never truly exists. Even in a sealed room, there is always a faint hum, a minimal vibration. The universe also has that background. Fossil radiation is its baseline noise, a constant presence that defines the minimum thermal level of the cosmos. What is fascinating is that this whisper is not random. It is not meaningless noise. It contains information. It is a frozen image of the universe when it was young, a thermal photograph taken at the precise moment when light was able to begin traveling freely. Every small variation in that radiation is a memory, a trace of how matter was distributed back then. You can imagine it like a surface of water that suddenly freezes. The ripples that existed at that instant become trapped in the ice. Even if the lake changes afterward, those initial marks remain. Fossil radiation works in a similar way. It preserves the irregularities of the early universe, expanded and smoothed by the passage of time, but still present. For billions of years, this whisper has passed through galaxies, voids, stars, planets, and even your own body, without asking permission and without leaving a visible trace. It does not interact easily. It is discreet, patient, almost shy, and yet it is one of the most powerful testimonies to the history of the universe. When its existence was discovered, it was not like finding a new star or a new planet. It was more like realizing that there had always been background music, so constant that no one had noticed it. Suddenly, the universe ceased to be merely a collection of objects and events. It revealed itself as a system with memory. Fossil radiation establishes a minimum temperature for the cosmos. No matter how empty or silent a place may be, there will always be that faint residual warmth. It is the thermal floor of the universe, the persistent memory of an era when everything was hotter, denser, closer together. This detail changes how you understand the deep cold of space. The vacuum is not completely empty. Silence is not total. There is always that background whisper, that faint radiation filling every corner. Even in the most remote places, where there are no nearby stars or visible galaxies, fossil radiation remains present, marking the slowest pulse of the cosmos. As the universe expands, this whisper becomes ever colder, weaker, more stretched. But it does not disappear. Expansion does not erase it. It only dilutes it. It is like a song playing in a room that keeps getting larger. The volume drops, but the melody remains. This thermal background also acts as a reference point. It allows us to measure how the universe has changed over time. By comparing its current temperature with what it must have had in the past, it is possible to reconstruct the history of expansion, to understand when certain transitions occurred, when the cosmos moved from one stage to another. There is something deeply human in this idea. We live surrounded by memories, some clear, others barely perceptible, but all of them influence who we are. The universe also has memory. It does not remember in a conscious sense, but it preserves physical traces of its past. Fossil radiation is one of those traces, perhaps the oldest we can detect directly. You do not need sophisticated instruments to grasp its meaning, only imagination. Knowing that, as you look at the night sky, a faint radiation is crossing everything, telling a silent story, changes how you perceive space. The universe stops being just a stage and becomes a discreet narrator. This whisper also connects all epochs of the cosmos. It does not belong only to the past. It exists now. It passes through you now, and it will continue to exist in the future, even if it becomes increasingly difficult to detect. It is a bridge between what was, what is, and what will be. Even stars, with all their heat and brilliance, cannot extinguish it. Fossil radiation remains, passing between them, indifferent to their cycles of birth and death. Galaxies form and disperse, but this background endures, like a slow breath that never stops. In a sense, fossil radiation is the true backdrop of the universe. Everything else unfolds upon it. Every structure, every thermal contrast, every point of light exists in a cosmos that still vibrates with that primordial echo. As you move forward in this story, you may begin to feel that the universe is not only vast in space, but deep in time. Fossil radiation is proof of that depth. It is a signal that has survived enormous transformations, radical changes, immense expansions. Fossil radiation is not just there as a passive memory of the past. It also functions as a kind of map, a silent guide that allows us to understand what the universe was like when it was still taking its first steps. It does not speak in words or point out directions explicitly, but if you learn how to read it, it reveals a surprisingly detailed story. It is like finding an ancient manuscript written in a strange language, where each symbol seems simple, but together they convey something profound. When observed carefully, that uniform whisper is not completely smooth. It has small variations, tiny temperature differences that break the apparent perfection. They are changes so subtle that they do not affect the general sense of uniformity, yet sufficient to mark real differences. Those variations are the imprints of the first irregularities of the cosmos, preserved as an echo that refuses to disappear. Imagine a wall painted white. From far away, it appears completely uniform. But as you get closer, you begin to notice shadows, slight changes in tone, almost invisible marks. Fossil radiation is something like that. At first glance, it is homogeneous, but when examined carefully, patterns emerge that tell how matter was distributed when the universe was young, and stars and galaxies did not yet exist. These variations did not arise later. They have been there since the moment the universe became transparent. They are the oldest record we have of how energy was distributed in primordial space. Each slightly warmer region indicates a place where there was a bit more matter. Each slightly cooler region marks where there was less. It is a simple language, but an incredibly precise one. What is fascinating is that by studying this pattern, it is possible to anticipate the future of the universe, not because it is written literally, but because those tiny differences guided the path gravity would later follow. Wherever fossil radiation shows a slight anomaly, the universe later built structures. Galaxies, clusters, filaments, all can be traced back to those initial differences. It is like observing tiny cracks in a newly paved road. At first, they are almost invisible, but over time, traffic and weather amplify them. Years later, those small imperfections have become clear grooves. The universe did something similar. It took minimal irregularities and allowed them to grow over billions of years. Fossil radiation also acts as a clock. By measuring its current temperature and comparing it with theoretical models, we can reconstruct how the universe has changed over time. It is a way of traveling backward without leaving the present, of peering into an era when everything was more compact, hotter, closer. This permanent whisper also carries something deeply comforting. In a universe where everything seems to change, where stars are born and die, where galaxies transform and drift apart, there is something that endures. Not intact, not immobile, but persistent. Fossil radiation has survived all the great cosmic transitions. It was there before the first stars, and it will still be there when many of them have gone out. As you listen to this, it is inevitable to think about the scale of time. Fossil radiation began its journey long before Earth existed, long before the sun formed, even before the first galaxies lit up space. And yet it is still present now, crossing this moment, connecting your present to a past that is almost inconceivable. It does not need to be spectacular to be important. It does not dazzle. It does not heat. It does not produce striking images. Its power lies in its constancy. It is a reminder that the universe has layers, that beneath everything we see lies a deeper, older, quieter history, no less real for being silent. It also teaches us something about the limits of knowledge. Fossil radiation marks how far we can see directly. Beyond it, the universe was opaque. There is no freely traveling light from before that moment. It is a natural boundary, a horizon separating what is observable from what can only be inferred. It is not an artificial barrier. It is a direct consequence of how the cosmos evolved. That boundary is not frustrating. It is revealing. It tells us that even the universe has moments when information becomes trapped, when the past cannot be observed directly. And yet, with what remains, with that faint whisper, it is possible to reconstruct an astonishingly rich history. Fossil radiation also unifies the sky. No matter where you look, you always find the same signal. It does not belong to a particular galaxy or a specific region. It is truly universal. In a cosmos full of contrasts and inequalities, this common background reminds us that everything shares a single origin. There is something poetic in thinking that the universe never stopped speaking about its childhood. It does so in a low voice, almost imperceptible, but constantly. Fossil radiation is that voice. It does not shout. It does not insist. It is simply there, waiting for someone to choose to listen. As the universe continues to expand, this whisper will weaken even further. It will stretch, cool, and become increasingly difficult to detect. In a distant future, it may disappear from the observational reach of any civilization, not because it ceases to exist, but because it becomes too faint. That makes the present a special moment, an era in which it is still possible to hear the echo of the origin. This thought changes the way the sky is seen. It is no longer just a space filled with distant lights. It is a living archive. Every bright point floats on a background that remembers a time before all visible light. The contrast between the stars and fossil radiation is the contrast between the young and the ancient, between the active and the persistent. In the end, fossil radiation is not only a scientific tool, it is an invitation to think of the universe as a continuous story, where nothing is ever completely lost, where even the oldest moments leave a trace. It is a reminder that the cosmos did not begin with silence, nor end with noise, but has always been filled with a soft, constant murmur, accompanying every stage of its evolution. There is a key moment in this story when everything changes, not because the universe does something different, but because the observer begins to understand their place within it. Looking at the sky is not a passive act. It is not simply receiving light. It is a form of time travel. Every time you lift your gaze, whether you realize it or not, you are going backward. The reason is simple and, at the same time, profoundly unsettling. Light is not instantaneous. It travels, and it does so at an enormous but finite speed. That means that everything you see is actually happening in the past. Even the light from the sun, so close and familiar, takes several minutes to arrive. If the sun were to disappear right now, you would still see it for a brief moment, like a silent farewell. When this idea is extended to the rest of the universe, the perspective changes completely. The stars that appear fixed and calm may have changed or even ceased to exist long ago. Distant galaxies are not observed as they are today, but as they were when the light that is now arriving began its journey. Looking far away is looking back, not as a metaphor, but as a physical reality. You can imagine it like observing a city from a distant mountain at night. The lights you see do not represent the exact present of every street. They represent different moments, minimal but real delays. In the universe, those distances are so vast that the delay is not measured in seconds or years, but in millions and billions of years. This turns the observer into something more than a witness. The observer becomes an archaeologist of time. Each arriving photon is a piece of the past that has survived an incredibly long journey. It carries not only information about where something was, but about when it was that way. When you look at a distant galaxy, you are not seeing a faraway object floating in the present. You are seeing an earlier stage of its life. Perhaps when that light departed, the galaxy was forming stars at a frantic rate. Or perhaps it was calm, slowly aging. The sky thus becomes a mosaic of overlapping epochs. This explains why the observable universe is not a frozen portrait, but a collection of moments. What is nearby appears more recent. What is far away appears older. On large scales, looking farther means getting closer to the origin, not because space is a time tunnel, but because light preserves memory. There is something deeply human in this idea. In everyday life, we also look back through traces, photographs, memories, marks. We never access the past directly, only what it left behind. The universe works the same way. We cannot observe its birth as a real-time event, but we can read its consequences imprinted in light. Fossil radiation is the extreme example of this. It is the oldest light we can observe directly. Beyond it, the universe becomes opaque, not because nothing existed, but because information could not travel freely. That limit places the observer in a privileged position. We live in an era in which it is still possible to see very far, and therefore very far back. The role of the observer is not to alter the universe, but to interpret it. Every measurement, every image of the deep sky is a reconstruction. It is not about seeing the universe as it is now, but about understanding how it was and how it came to be this way. The present of the cosmos is not observed directly. It is inferred from layers of the past. This way of looking demands patience. There are no instant answers. Every signal that arrives has been shaped by time, by the expansion of space, by interactions with matter and energy. To observe is to accept that one always arrives late, but that even so, what is received is valuable. It also changes the relationship with cosmic cold and heat. When extremely cold or extremely hot regions are observed, what is being seen is not a current condition, but a specific stage of their evolution. A deep void observed today may have been denser in the past. A bright region may have been much hotter when it emitted the light that is now arriving. The observer, then, is not external to the story. They are part of it. They live at a point in time from which a unique slice of the cosmic past is accessible. At another moment in the universe, that slice would not be visible. Before, there were no observers. Later, there may no longer be enough accessible information. Looking back is not nostalgia. It is understanding. It is recognizing that everything that exists has a history, and that this history is never completely erased. It remains traveling, diluting, cooling, but never disappearing entirely. Every time a telescope is pointed at the deep sky, it is not only distance that is being sought, it is time. A narrative is being reconstructed in which the young, hot, dense universe coexists in the same image with the colder, larger, quieter universe. The role of the observer is to unite those layers, to give them meaning, to understand that the sky is not a static stage but a sequence, that the extreme cold of present-day space is the result of a burning past, that the silence that now dominates was preceded by an intense murmur of interacting particles. In the end, looking at the universe is also looking at oneself on a different scale. It is accepting that the experience of the present is always woven with traces of the past, that nothing is observed as it is now, but as it was when it left its signal. If you observe the universe as it is today, with everything we have covered so far in mind, you begin to notice a clear and almost inevitable pattern. The present-day cosmos is, in essence, a cold place. Not cold like a winter night on Earth, but cold in a much deeper sense. A cold that dominates almost the entire volume of space. A cold that stretches unobstructed between galaxies, between stars, between solitary particles wandering for millions of years without encountering anything. The average temperature of the universe is extremely low. Most of the time, in most places, nothing spectacular happens. There are no explosions, no intense light, no sustained heat. There is stillness. There is expansion. There is energy slowly diluting. That is the natural state of the current universe. Cold is not the exception, it is the rule. And yet, that same universe is dotted with regions where this rule is broken. Small points, comparatively tiny, where energy concentrates, where matter organizes, where heat resurges with force. These are islands of energy, stars, stellar systems, entire galaxies shining like luminous archipelagos in a dark, frozen ocean. You can imagine it like an immense sea at night. The surface is cold, silent, apparently uniform. But here and there, active volcanic islands appear, places where the planet's interior pushes outward, where there is heat, movement, and transformation. The universe works in a similar way. Cold dominates, but it does not rule without resistance. These islands of energy are not accidental. They exist because, at some moment in the past, certain regions had a slight advantage, a bit more density, a bit more matter, a minimal irregularity that gravity patiently amplified. Over time, those regions detached themselves from the general cooling and began to collapse, to heat up, to shine. What is interesting is that these islands are not distributed uniformly. They cluster, forming larger structures, gigantic networks of filaments and clusters. Between them lie enormous voids where the cold is even deeper, where expansion has stretched matter until it nearly disappears. The present-day universe is a mixture of extremes, highly active zones coexisting with regions that are almost dead. When you look at a galaxy, what you see is one of those islands, billions of stars grouped together, each generating heat in its core, each locally fighting against global cooling. But even within a galaxy, the contrast persists. Between the stars, space remains cold. Energy is not distributed homogeneously. It concentrates, dissipates, and concentrates again in long cycles. This panorama changes the way we understand the universe. It is not a thermally balanced place. It does not seek a uniform temperature. It is permanently unbalanced. Cold gains ground on large scales, while heat resists in small regions. It is a silent, slow, but constant competition. Stars are the visible protagonists of this resistance. In their cores, temperatures reach millions of degrees. Matter moves at enormous speeds. Energy is released without rest. And all of this happens while, just a few light years away, space remains close to absolute zero. The contrast is so great that it is hard to imagine without resorting to analogies. Think of a spark lit in the middle of a frozen desert. The spark cannot warm the entire desert, but while it exists, it creates a different environment around it. It allows reactions, changes, processes that could not occur in absolute cold. Stars fulfill exactly that role. These islands of energy are also temporary. No star is eternal. All are born, live, and die. Some do so quickly, others over billions of years, but all eventually go out. When that happens, the cold reclaims that territory. The universe does not accumulate heat indefinitely, it loses it. The expansion of space plays a key role here. As the universe expands, energy is stretched and diluted. Even radiation cools over time. This means that, although stars will continue to be born for a long time, the overall balance favors cold. Each new island of energy is a local victory, but the global picture continues to tilt toward thermal stillness. This process is not dramatic. There is no specific moment when the universe suddenly becomes cold. It is a gradual cooling, almost imperceptible from a human perspective. But on cosmic scales, it is inexorable. The present universe is already much colder than it was in the past, and it will continue to cool. Even so, these islands of energy are crucial. Without them, the universe would be a simple, repetitive place, almost empty of interesting events. It is in these regions that complexity occurs, where elements combine, where chemistry becomes rich, where structures capable of sustaining long and delicate processes appear. Every planet, every atmosphere, every possible form of life depends on the existence of these thermal islands. They are refuges from the dominant cold, places where energy remains concentrated long enough for something more than solitary particles to exist. But even within these refuges, cold never disappears entirely. It is part of the environment, the night, the shadow, the void between objects. Stellar heat always coexists with cold regions. The balance is dynamic, never complete. This contrast defines the character of the present universe. It is neither a blazing place nor a completely frozen one. It is a stage of gentle but persistent tensions. Energy flows from where it is concentrated to where it is lacking, and in that flow, cosmic stories are written. As you listen to this part of the story, you may begin to notice that cold is no longer just an absence of heat. It is a context. It is the background against which the universe allows exceptions to exist. Without that cold background, islands of energy would not stand out, would not have clear boundaries, would not be able to maintain their identity. When this universe full of islands of energy is observed closely, it becomes clear that none of them truly exists alone. Although cold dominates the space between them, there is a silent connection that does not require heat or light to function. An invisible network sustained by gravity, crossing the void and organizing matter even where nothing seems to be happening. Galaxies do not appear randomly distributed. They cluster along enormous filaments, forming structures reminiscent of a cosmic web, where bright regions align like knots, and between them lie immense, deep regions that are increasingly cold and stripped. It is like looking at a nighttime map from very far away. where illuminated cities are connected by invisible routes, while entire expanses remain in darkness. At these meeting points between islands, energy concentrates again. When galaxies approach one another, gas is compressed, temperature rises, and new stellar births are triggered. Even in a universe that is mostly cold, motion and interaction continue to create moments of intensity, reminding us that global cooling does not mean absolute immobility. However, each of these episodes comes at a cost. Cold gas, necessary for forming stars, is not infinite. Over time, it is consumed, heated, or dispersed, and the islands of energy begin to change in character. They continue to exist. They continue to shine, but no longer with the vitality of their earliest stages. The present universe is active, yes, but it is also a universe that has left its youth behind. Accelerated expansion reinforces this process. The islands move away from one another at an ever-increasing rate, to the point where many will fall out of permanent contact. It is not that they disappear, it is that the space between them grows too fast. The light that today travels freely will not always be able to do so. Cold will not only dominate thermally, it will also dominate through isolation. In that distant future, each island will be almost a closed world, surrounded by an ocean of space so cold and vast that the rest of the universe will lie beyond reach. But even now, that separation is already underway. Many of the galaxies we see today are already moving away forever, and their light is, in a sense, a prolonged farewell. Even so, this scenario is not empty or devoid of meaning. The contrast between dominant cold and islands of energy creates diversity, history, and complexity. Cold allows stability and duration. Heat drives change. Neither fully dominates. They need each other for the universe to be more than a uniform space. From this perspective, the place we inhabit becomes extraordinary. We live in a chain of thermal exceptions, a planet warmed by a stable star within an active galaxy, in a universe that is mostly cold and silent. Everything we know depends on that delicate imbalance. The cold that surrounds these islands is not an enemy. It is the background that defines them. Without it, heat would have no form, no contrast, no structure. The universe moves forward not by eliminating extremes, but by allowing them to coexist. Over time, the islands will continue to fade slowly. The luminous map of the cosmos will become simpler and more dispersed. But during this long intermediate stage, the universe offers an enormous richness of scenarios, where deep cold and concentrated energy together write the story. Thus, the present universe is not just a cold place with a few bright spots. It is a system in constant tension, where silence and activity coexist, where global cooling does not prevent moments of intensity from arising, and where each point of light represents a temporary victory against the frozen immensity that surrounds it. There comes a point in this story where cold ceases to be merely a consequence of the passage of time and becomes an active protagonist. We are no longer speaking only of a universe that cools because it expands, but of places where cold reaches such extreme levels that they seem to defy intuition. Regions where energy is so scarce that even the concept of motion becomes almost abstract. To understand these places, it helps to leave behind the everyday idea of cold. On Earth, cold is always relative. Even in the iciest environments, there are vibrating molecules, residual heat, exchange. In the universe, by contrast, there are scenarios where that vibration is reduced to the minimum imaginable, where temperature approaches a limit that is not cultural or technological, but physical. That limit is absolute zero. It is not a place one reaches by walking, nor a point in space that can be pointed to, but a conceptual boundary. It represents the state in which particles possess the least possible energy. They are not completely motionless, because physics does not allow that, but they are so close to that state that any classical notion of heat ceases to make sense. What is interesting is that the universe does not need effort to approach this limit. While in terrestrial laboratories, extreme technologies are required to reach temperatures near absolute zero, the cosmos does it naturally. It is enough to let space expand, let energy dilute, let matter slowly separate. Deep cold is not an anomaly. It is the simplest destiny. In the great cosmic voids, those immense spaces between clusters of galaxies, the temperature comes ever closer to that limit. There is almost no matter there, almost no radiation, almost no interaction. They are regions where the universe seems to have withdrawn, leaving only a faint thermal background as a witness to its more active past. You can imagine these voids as gigantic abandoned rooms, where the air has slowly leaked out, where nothing remains to generate noise or heat. They are not violent or dramatic scenes. They are silent, stable, patient. Cold there does not destroy. It simply remains. These types of regions are not rare. In fact, they occupy most of the volume of the universe. Galaxies, stars, nebulae, everything we usually associate with activity and energy is confined to a tiny fraction of total space. The rest is the domain of extreme cold. However, even in these seemingly empty places, there is history. Cold is not synonymous with absence of a past. Each void preserves the imprint of how matter was distributed in the early stages of the universe. They are the result of a slow process in which gravity drew matter out of some regions and concentrated it in others, leaving behind increasingly stripped zones. This process does not occur abruptly. It is gradual, almost imperceptible. Over billions of years, small initial differences are amplified. Where there was a bit less matter, expansion acts more freely. Space stretches faster. Density drops. Temperature falls even further. Cold deepens. At this point, cold is no longer just a passive consequence of expansion, but a condition that reinforces the structure of the universe. Cold regions remain stable because there is not enough energy to alter their state. They become the permanent backdrop against which everything else occurs. There is something almost meditative about thinking of these places. There is no intense light, no spectacular events, no explosions, and yet they are essential. Without them, the universe would have no contrast. There would be no way to distinguish islands of energy. Deep cold is what allows heat to stand out. Moreover, these extreme scenarios help us understand the extent to which the universe preserves memory. Even in the coldest void, fossil radiation is still present, stretched, cooled, but not erased. It is a sign that no place is completely disconnected from the origin. Some of the coldest known places are not necessarily found in the largest voids, but in very specific situations where local physics pushes the temperature even lower. They are exceptions within an already cold universe, cases where particular processes allow thermal energy to dissipate with extraordinary efficiency. These scenarios show that cold is not uniform. It has degrees, nuances, different histories. There is a cold associated with the general expansion of the cosmos, and another linked to very precise local dynamics. Both coexist, overlap, and enrich the thermal narrative of the universe. What unites all these places is a simple but powerful idea. The universe does not seek thermal equilibrium quickly. It does not rush toward a final state. It slides slowly, allowing very different regions to exist along the way. Extreme cold does not cancel diversity, it sustains it. As we move through this section, it becomes clear that talking about the coldest places in the universe is not just about listing minimum temperatures. It is about exploring scenarios where time seems to pass differently, where the absence of energy slows processes to the point of near stillness. When you approach the coldest places in the universe, you discover that not all of them are alike. Cold is not a single uniform landscape, but a family of different states, each born from very specific conditions. Some exist because space has expanded and energy has diluted over billions of years. Others appear because certain physical processes push temperature toward unexpected limits, as if the cosmos had found shortcuts toward the lowest possible state. One of these scenarios arises when matter becomes so dispersed that interactions become exceedingly rare. In those regions, atoms may take years, centuries, or more to encounter another atom. Without collisions, without exchange, the concept of temperature loses its everyday character. There is no classical thermometer that can adequately describe what is happening. Cold there is not felt, it is inferred. Think of a gigantic hall, empty, where there is only one person walking very slowly. The air is so scarce that it barely exists. Is it cold? The question almost ceases to make sense. In the universe, there are places like this, where the notion of heat is no longer experienced as something that transfers, but as an almost abstract state. There are also regions where cold arises after extremely energetic events. It seems contradictory, but it is not. When a cosmic explosion ejects material into space, that material expands rapidly. As it expands, it cools. In some cases, this cooling is so efficient that the resulting temperature drops below that of the surrounding environment. Here, cold is a direct consequence of a violent release of energy. This type of cooling is reminiscent of what happens when you quickly open a gas valve. The gas rushes out, expands, and cools. On cosmic scales, the same principle applies, only with immense distances and prolonged times. The result is pockets of extremely cold matter embedded in a universe that is already cold to begin with. There are also places where radiation has been stretched to almost unimaginable extremes. As space expands, wavelengths lengthen, energy decreases, and effective temperature drops. In especially isolated regions, where there are no nearby energy sources, this stretched radiation defines the dominant thermal level. There, cold does not come from the absence of matter, but from the absence of energy renewal. These extreme scenarios help clarify a key idea. The universe does not have a switch that simply marks cold or hot. It has processes, and each process leaves its thermal imprint. Where gravity gathers matter, heat appears. Where expansion dominates, cold deepens. Where there is no interaction, temperature becomes a limiting concept. Sometimes, the most intense cold is not found in the most distant places, but in very specific corners where conditions align perfectly. They are exceptions within exceptions. They do not define the universe, but they enrich it. They show how far physics can go when given enough time and space. These places also force us to rethink what we mean by vacuum. It is not simply absence. It is an active, dynamic state with its own properties. The cold vacuum of the universe is not nothing. It is something very precise, with a minimal energy, with tiny fluctuations, with a structure that influences what can exist within it. As you pause to think about these scenarios, cold ceases to be a threat or an ending. It becomes an archive. In deep cold, processes slow down so much that traces of the past can survive for immense periods of time. It is a natural preservative, a silent guardian of ancient states. This role of cold as a preservative is fundamental to understanding why the universe maintains memory. Without it, everything would be too dynamic, too ephemeral. Heat would transform everything too quickly. Cold allows structures, once formed, to persist, even if only faintly. Viewed from this perspective, the coldest places in the universe are not the most empty of meaning. They are the most stable, the least altered. There, time seems to flow at a different pace, not because the laws change, but because almost nothing happens to mark its passage. Even so, these places are not completely isolated from the rest of the cosmos. Expansion connects them. Fossil radiation passes through them. Gravity integrates them into the overall structure. They are extremes, yes, but they are not outside of history. They are part of it. Over time, the universe will increasingly tend toward these states. Energy sources will slowly shut down. Interactions will become rarer. Deep cold will cease to be a feature of specific regions and will become the dominant condition almost everywhere. Not suddenly, not dramatically, but with implacable calm. Thinking about this is not thinking about an abrupt end, but about a prolonged transition, a universe that slowly goes dark, not because something fails, but because it has followed its natural course. Extreme cold is not a punishment or a mistake. It is the logical result of a cosmos that has had enough time to expand and cool.